I'm honored to be here today to be able to speak on the topic of fire risk and fire management inside a lithium energy storage system. I'm going to start off today by showing you a video of doing something really fun. We're going to blow up a battery. So please watch this and let me know what you think. That was pretty dramatic. Now imagine that was a single cell, 75 amp hour, being forced into a thermal runaway. And a single megawatt hour system, you have around 3,900 of these cells that we have to manage safely through the event that you just saw on the screen. It's a pretty big challenge when you consider these vessels run almost continuously, multiple trips a day for 10 years and even up to 30 years. So the challenge is here. Now I'm going to show you a video of what we in the battery industry have brought to the table in terms of being able to manage this very risk. We're going to perform what's called a nail penetration test, perhaps the most dangerous thing you can possibly do. With all mechanical, electrical, and software safeties taken away, this is a direct example of how a cooling system can manage the most dangerous event within a cell, a completely spontaneous combustion. So please watch. By the way, unless you have the absolute confidence of your product, don't punch nails into it in this manner. It's not very safe. So what you see here is the exact same event that you saw in the video a second ago. That cell is about 800 degrees right now, and it is failing dramatically, but in a managed way. All that we're producing is the gas. And that gas is going to be about 200 liters. That is the reaction of the entire cell combusting at the same time. The important question is what happens to cell number 2. So what you see here is a picture of the cell that was failed with the nail penetration test on the left that ran at about 800 degrees, and you have the picture of cell number 2 in absolutely perfect shape other than a little bit of smoke damage to the top part of the cell that only got up to about 80 degrees. Within an hour, the cooling system had brought the temperature of both cells down to 24 degrees Celsius again, the temperature of the cooling water. So this is a really, really good example that even though the risk is massive and the fire and the damage that can cause is terrible, it can actually be managed safely within a battery system. So how do we do that? We take a look at all the risks concerned. One is choosing the correct cell and the right materials. The other is how do we design a battery? What decisions do we make? How do we install it? How do we commission it? How do we operate it? Then how do we service and train people to be able to support it? So we'll talk a little bit about these topics. Cell selection is absolutely critical. How many connections are you managing? In our case, 3,900 cells makes up 1 megawatt hour. If I were to use an 18650 cell, perfectly good product, but to get 1 megawatt hour, I need 167,500 of the cells that are the 18650s. The more number of cells you have, the greater the risk. Then we have to worry about charge of efficiency. So heat is the killer of batteries on every aspect of it. They make it much more difficult to manage safety. They make it much more difficult to manage aging. So the internal resistance of the cell becomes a very critical factor. What are the internal resistance numbers for your cells, not only brand new, but how do they age? There's no escaping physics here, and we have to deal with this. Then you have to look at how does the cell manufacturer support you. Given it's the single biggest component in your battery, do they give you a back-to-back warranty for the full 10-year life that everybody's asking your system to engineer? It's a question to be asked. The other thing to understand, there hasn't been a marine system operating for 10 years yet. This is a whole new space. We have been learning a tremendous amount, and the uptake has put a lot of pressure on all of us to be able to deliver these systems safely, but the truth is, we're at the beginning of this industry. Now we actually get to the point of designing a battery. So, do you go air-cooled versus liquid-cooled, or some combination of the two? The question is, can air-cooled keep up with the heat generated by the cells, or do you have to oversize your system to manage the C rates and the heat that you generate in order to give yourself something that can last 10 years? Then we have to talk about what we're doing at the terminals. Many batteries are manufactured with live terminals. When you're dealing with 1,000 volt, that's a lot of risk. We put in contactors to keep that risk down to 100 volts and to actually make sure there is no power at the terminals until we've connected all the cables and engaged with the system. It's a much safer way to service the battery that nobody can be shocked. Then we talk about motorized breakers, fuses, how are they engaged within the system. We put a motorized breaker at the controller along with fuses depending upon the power electronics package. It helps keep our crew safe. Now, one of the most important aspects in this topic, firefighting equipment. There's some fantastic firefighting third-party systems available if your battery doesn't have that capability internally. But you have to make sure that third-party system completely understands the risk of managing not only the initial firefighting of the system, but the long-term issue that lithium fires can go on for days and days and days. And the risk has to be managed within that context of time. Then we talk about cells and design in either series or parallel, and we don't go down the road of parallel cells anymore. It gives you more energy density and reduces cost to a certain degree, but we believe you need to be able to manage a cell on a cell level in a system no matter how big it is, and that's very important. So what we do is we actually attach a voltage and temperature sensor to each and every single cell within a system so that we can not only manage charge and discharge of the cell, but we can manage the state of health of the cells and the performance and measure the risk of the cells as they age. The next question is, how well protected is your battery from the environment? IP67 is a pretty good insurance policy against a 10-year life on a system. Then how do we extract gas? So when a battery fails, it can produce, as you saw, a tremendous amount of gas. We believe the best philosophy here for safe management and operation and risk prevention is to extract that gas from the battery space without having it enter the battery space. So effectively your battery module becomes your battery room. If we can do this, then you can enter the room through a full failure, as you saw in our video earlier, and still engage with disconnection, removing power cables, doing anything you need to in the room to help mitigate any potential damage here. Next question, integration and software. So how good is your BMS? Are you using your own? Are you buying one from somebody else? How much experience do you have to understand all the problems that you can have with your own software in order to deliver a system that's going to operate safely? And when you integrate, how well does it tie into the power management system of the vessel? There's a lot of questions to be asked, and the designation and the integration of the software will have a massive effect on the ability to measure the performance, the safety, the alarms, and manage and deliver a safe system for the operators. Then there's the question of how do we manage safety over time with software. And what we've done by having a voltage and temperature sensor on each cell is we have the ability to measure the state of health of each cell all the time. We've also developed algorithms that will measure the actual internal resistance of the cells as they age so that we can accurately predict when the cells are going to fail. The best way for us to avoid a fire risk or an explosion risk is simply to eliminate the issue before it can even become a risk. Then, how do we monitor the system itself? When you take a look at today what we can do with analytic data, there's a tremendous amount of information that can be presented on the screen, whether it's on your phone, on your laptop, on your tablet, at your master computer engineering station on board the ship. And that data can help give the crew a clear understanding of the performance of the system, and you can analyze all the historical data all the time. We can again predict the aging and the performance of the system. And the best way to avoid the risk of fire is to actually manage that prediction and accurately take action that's going to prevent the battery from being put at risk. The service of the vessel is a key element for us as well. These are not complicated machines, but they are very sophisticated in the risk that they present. So being able to visually inspect all of your power terminals, your water terminals, your communications terminals, and to be able to actually access the data within the battery, at the battery, we think is very important for being able to manage the safety of the system. When your crew can do this, they're going to gain confidence in the actual safety and operation of the boat. Then there's training. We believe that training and more training is the right way to manage issues and episodes like fires and explosions. If we can do this, we can deliver a safe battery system to everybody at the end of the day that will last years and years and years. I'd like to thank you all very, very much.